Problem 6, if the product hx, okay, is fx times gx, is continuous at 0. Okay, first, what does continuous mean? Okay, I think on the graph it's very obvious. Okay, let's draw a function. Maybe this function looks like this. Okay, and let's call this point A, let's call this point B. Okay, so this function is a piecewise function, right? Then the question is this function continuous at the point A? Is this piecewise function continuous at this point A? The answer is yes, because continuous, in a very simple term, is just when you draw the function, your pen just never leaves the screen. Then at those points, the function is continuous. Okay. But you see, at this point B, you want to keep drawing this function, but now it's like a jump point, right? At this point, it suddenly jumped from here to here, right? And then you keep drawing. So this point, at point B, fx is not continuous. Okay, but again, it's math, so what does that really mean? So fx is continuous at a point A, right? This means, okay, this double direction arrow just means if and only if. Okay, that means two statements, they are equivalent. Okay, for example, a number is positive is equivalent of saying that the number is non-negative. Okay, there are just different ways of telling you the same thing. So fx continues at A if and only if fa is equal to the limit of fx, right, when x is approaching A. Okay. So here we have, actually this equation means a lot. Okay, there are three things, right? There are three things in this equation. Okay, first thing, right, your fa must exist. Okay, so for some function at some point, the value doesn't even exist, right? So here it's fa is equal to the right-hand side. That implies fa already exists. Okay, that implies fa already exists. So same thing, your limit must exist, right? Again, we see the function. For example, this sample function here. At this point, the limit doesn't exist, right? Because the limit from the right is different from the limit from the left. So here it implies that the limit must exist. Okay, and then the third thing is their value must be the same, right? Right. The third thing is their value must be the same. Okay. So this is continuity. All right. So problem 6, if hx is equal to fx times gx, right, and it is continuous at 0. Okay, so I think do it down here. Right? This is okay. This is continuity. So fx times gx is continuous at 0. Is it always true that both fx and gx must be continuous at 0? And why? Okay. Here, okay, one thing is very clear. Okay, hx is continuous when x is equal to 0, but it is a product of two individual functions. Okay, and you don't know what they look like. Okay, a natural, when you see the product, okay, and you think about continuous, sometimes it's about this type of jump point, right? When you are at the jump point, the function is not continuous. But since it's a product, right? So you can see even the individual function has a jump point because it's a product of two functions. They could have different jump points, and they could, compensate each other and make the product continuous. Okay. For example, what do I mean? Let's say this is a very easy piecewise function. Okay, the function is 0 when x is non-negative. Okay, this means when x is 0, the function is also 0. Okay, and when x is positive, it is 1. Okay, so let's say this function is our fx. So fx is 0 when x is non-positive. Okay, your fx is 1 when x is positive. Okay, it is a piecewise function, and very obviously we can say that when x is 0, this function is not continuous. Right? This function is not continuous because when you draw the function at this point, you have to lift your pen, move it to here, and keep drawing. Right? Or you can apply the former definition. You can say that at this 0, right, the limit doesn't even exist. Okay, the limit of fx doesn't even exist because the limit from the right is different from the limit from the left at this point. Okay, so this is our fx. And under the same concept, you can construct another function, okay, and it's like the opposite of fx. Let's say this function, it is 1. Let's call this gx. Okay, you can see this gx, it is 1 when x is smaller than 0. It is 1 when x is negative. It is 0 when x is non-negative. Okay, and for the same logic, this function is not continuous at 0. Right. But you can see their product. Now it's where, right, when we multiply them, now it's different. Okay. So first thing, when x is smaller than 0, right, when x is smaller than 0, your fx is 0, right, or gx is 1. So your fx times gx is 0 times 1. Okay, when x is equal to 0, again, your fx is 0, your fx is 0, your gx is also 0. Okay, and when your x is greater than 0, your fx is 1, but your gx is 0. Okay, so you can see that it's no matter x is negative, positive, or 0, it's always 0. Right, so this product is just a 0 function. So your fx times gx, which we call it an hx, is just always 0. Okay, for any x. So it's a constant function. And it's a constant function, it's always continuous. Right, you draw it. Okay, it's very easy to draw. It's just a constant function. This is your hx, which is fx times gx. So this constant function is continuous at 0. Right, so that's a counterexample for problem 6. You can see the product is continuous, but each individual function is not continuous at 0. Okay, let me write it down. So hx is continuous at 0, right? But neither fx nor gx, they are both not continuous. Right, so this is a counterexample of the statement in problem 6. Okay, so the statement in problem 6, it's false. It is false.